Hi, this is Krishna. So I'll now prove this identity. Laplace of f dash is equals to s into Laplace of f minus f of 0. We know the formula for finding Laplace of a function f of t, which is Laplace of f of t is equals to integral 0 to infinity e power minus st into f of t dt. So in the similar fashion, we will substitute, in place of f of t, we'll take f dash of t and simplify to get the result. So L of f dash of t is equals to Laplace of f dash of t is equals to Laplace of df by dt, which equal to integral 0 to infinity e power minus st into df by dt into dt. This can be simplified by using integration by parts, and for that let's assume e power minus st as the first function u and df by dt into dt as the second function v. Applying the integration by parts formula, we will get Laplace of f dash of t equal to e power minus st integral 0 to infinity df by dt into dt minus integral 0 to infinity minus s e power minus st into integral df by dt into dt. Now let's simplify this. E power minus st and now for further simplification, we don't know what this function f of t is, and as we are not aware of this, and so we can't substitute infinity in place of t and then just directly solve it and write f of infinity minus f of 0. That can't be done. So instead what we're supposed to do is to apply limits to this function f of t. So we will write limit t tends to infinity e power minus st into f of t. So this is a simplification of this term, minus e power minus s into 0 into f of 0 minus integral 0 to infinity, plus s e power minus st f of t dt. We can substitute 0 directly, but we can't substitute infinity, as infinity is not defined. So if you substitute 0, you know what f of 0 could be, but f of infinity can't be defined, and hence we apply the limit. And now on further simplification, limit t tends to infinity e power minus st f of t minus this becomes 1 f of 0 plus s into integral 0 to infinity e power minus st into f of t dt. This is s, it's not 6, I'm sorry. Yes. And now we'll have to make a small assumption, or it's more like, in order to define this limit, what we assume is if f is of exponential order, Now, what does this statement mean? If f is of exponential order, is that if the function f of t is of exponential order, which is it either increases or decreases exponentially when its terms are of the exponential order e to the power of something, only then can we define this limit. and and yeah, so when f is of exponential order s naught, we will have limit t tends to infinity e power minus st f of t is equals to 0 for all s greater than s naught. For any value of s which is greater than s naught, greater than the exponential order s naught, only then that this limit equal to infinity. And on this very condition, on this same condition where s is greater than s naught, even the Laplace of a function f of t will equal to integral 0 to infinity f of t into e power minus st dt for s greater than s naught. So for this condition is very important, for both the what do you say, the first formula that we the Laplace of any function f of t formula that we define, and using this that we find the Laplace of f dash, and also for existence of this limit t tends to infinity e power minus st into f of t, and that for this condition turns out to be 0, and hence Laplace of f dash of t equal to limit t tends to infinity e power minus st into f of t minus f of 0 plus s into 0 to infinity e power minus st f of t dt equals, this is 0 for the condition that f is a exponential order function of s naught, and where this s is greater than s naught, minus f0 plus s into, we know that this is nothing but Laplace of f of t so which implies Laplace of f dash of t equal to s into Laplace of f of t minus f of 0, or in simple terms we can write it as Laplace of f dash equal to s into Laplace of f minus f0. Hence proved. Thank you.